Okay, so we're continuing number 2, and this is step 2. And so we found our eigenvalues in the first step, so now we want to find our associated eigenvectors. And since we obtained 2 eigenvalues, we should get 2 eigenvectors. So I'm just calling them V1 and V2, right, where V1 and V2 are bold. And these vectors are going to be linearly independent, and it's not always possible, but in this case they're going to end up being linearly independent. Okay, so let's go ahead and find our eigenvectors using the eigenvector equation. So we have AV equals lambda V, which implies this is really AV minus lambda V equals 0. And if I factor out a V actually, on the right hand side, I get A minus lambda, and then I have the identity matrix times my vector V. So these are, I mean, this is the same equation, right? I just moved things around. But I want to use this specific equation because we really worked with A minus lambda I in the first step, but now we actually know a specific lambda. So we know that if from step 1, lambda 1, right, I believe I called that lambda 1 was 4. If lambda 1 is 4, then, okay, so then I have, okay, my A, and my matrix A is, again, 2, 3, 2, 1, minus lambda, which is 4, times the identity matrix. And, of course, that's times my vector V. And actually, let's go ahead and write my vector. Well, I'll do it in the next step, actually. So this guy, where we're just going to do scalar multiplication. And so I get 2, 3, 2, 1, plus, and then I get negative 4, 0, 0, negative 4. And notice, I mean, I'm writing, you can use brackets for matrices, or you can use parentheses for matrices. It doesn't really matter. Pick your preference. Times our vector, our eigenvector that we want to find, and I'm going to call that AB, and equals 0. These guys should have my little vector notation there. And vector addition, this is pretty easy, right? 2 plus negative 4, so that's negative 2, 3, and 0, so that's 3, 2, and then I get negative 3, and times AB, and this is really 0, 0 on this side, and I actually should be consistent here. It's not technically wrong, but it looks nicer when we're consistent. So this is what we have, and this should remind you, this is a system of linear equations in 2 variables from Algebra 1. So I mean, this is, if I multiply this 2 by 2 matrix by this 2 by 1 matrix, I get the following. Negative 2, right, so I'm doing row times column, row times column. So I get negative 2a plus 3b, right, and this is all really equal to 0. And I get 2a minus 3b equals 0. Okay, so this is a system, right, of linear equations. I mean, again, I went from matrices, right, to non-matrices. And you've solved many of these systems in algebra. You can use substitution, elimination, you know, Gaussian eliminate. You can use matrices, obviously, but this is a 2 by 2. This is very easy. So I'm going to go ahead and use the addition method. Why? Because when I add vertically, I get 0. I get 0. So all of that cancels, and I get 0. And obviously, right, 0 plus 0 is 0. So my variables are eliminated. So this is a true statement, right? 0 does equal 0. So remember, from algebra, you have 3 cases. You can have a unique solution, you can have no solution where there are parallel lines, or you can have infinitely many solutions. So infinitely many solutions. I mean, if you graph this line, it's really the same as this line, if that helps. I mean, if you graph it, it's going to be the same line. Okay, but we want to find our eigenvector, right? A general eigenvector. So I'm going to go ahead and rewrite. So when you get a true statement, this is what you do. I'm going to go ahead and take, I'll just take this guy. You can take any one. It's, again, they're the same line. I'm going to say negative 2 a plus 3b equals 0. And I'm going to go ahead and solve for b. And so if I solve for b, okay, so we get this guy and then solve for b, and we get 2/3 a. Okay, so b is 2/3 of whatever a is. Okay, so what's a? Well, a could be anything, since we have infinitely many solutions. So let's write thus. So our associated vector v1 that we want to find, that's a comma, right? And that's the arrow. We have is, okay, so this guy is your A and this guy is your B. Well, let's go ahead and write it in. Doesn't hurt to write it in. So let's give A a value. Well, if again, A can be anything. I'm going to let A be 3. Why? Because if A is 3, then B is 2. So if A is 3, then B is 2. So I get 3, 2, right? And the book writes it as 3, comma 2 transpose, right? Because the transpose of this row vector is the column vector, but the book wants to save space when they publish the book, so they actually don't write the column vector. But I mean, if they write this, it's the same thing. Okay, so let's find the second associated eigenvector. So similarly, okay, now we're working with our second eigenvalue. So our second eigenvalue was negative 1. So if lambda equals negative 1, then what is our, then a minus, right, lambda I, we're using the same equation, equals 0. And the nice thing is we already computed this guy, right? This matrix actually is, I mean, if you want to write it in already, I went ahead and just did the steps in the beginning since it was the first one. But when we calculated this, or simplify this, we said this was 2 minus lambda, 3, 2, and then 1 minus lambda. And then we had our A, B equals, and then, well, let's go ahead and just write the zeros. So we have this from step 1, or the very beginning of part of the problem. So again, this is our matrix equation, and what's lambda in this case? So here's my lambda. So I'm just going to go ahead and plug in my lambda here, so I can actually get numerical values. And so I get 2 minus minus 1, right? That's just 3, right? 2 minus minus 1, that's 2 plus 1, 3, 3, 2, and then again 1 minus minus 1 is 2. And I get my A, B, 0, 0. And again, this is just 3a plus 3b equals 0, 2a plus 2b equals 0. And here, I mean, we don't have to simplify, but it's, I mean, hopefully you guys can see that if I divide by 3, right, in the first equation, if I divide by 2 in the second equation, right, they're the same equation. So, I mean, this is obviously going to be, right, these are true statements. If you subtract the equations, right, if you do this, right, you get 0 equals 0. But, I mean, if you know they're the same, hopefully you see that, then it's obviously a true statement. We have infinitely many solutions. So thus, our associated vector, v2, with our eigenvalue of negative 1. So we have our A and B again, so A and B. Okay, from here, let's see, let's do it in maybe purple. So here I'm going to solve for B. You can solve for A. I'm just going to solve for B, and we know that B is equal to negative A. All right, we know that relationship. So again, if A is, you can pick any number you want. If A is, I don't know, 1, then B is negative 1. Okay, which is the same thing as 1 comma negative 1 transpose. And again, there are infinitely many solutions here there, I mean, oops, if you wanted to pick 2, this would be -2. If you wanted to pick 100, this would be -100. So there, again, infinitely many solutions because this line, let's see, we have b equals -a. I mean, this really looks like, I mean, this is really y equals -x. So there's our y equals -x line. And 1, -1, right, is right there. Well, if you pick 2, -2, 3, -3, -1, 1, I mean, there are infinitely many points. I just happen to pick that one. Okay, so again, you can pick your own value if you'd like. Okay, so we have 2 solutions, and okay, so remember the goal of this problem was to find the general solution, right? Because we didn't have initial conditions, the general solution of this differential equation. So I'm looking again on page 368 of your book, and so we did step 1, step 2, step 3, and notice that our general solution, right, of, right, these are all bold, right? So A equals AX is the following. It is, so we have x bold of t equals c1x 1 of t plus c2 x, that's an x of x2 of t, and then it goes plus dot 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 to cn x to the n, but our n here is 2 because we have 2 eigenvectors. So from here, this is just, so we have c1, right? But what's my x1? Well, from theorem 1, our x of t is our v e to the lambda t. So I'm going to go ahead and write v e to the lambda t, right? Where obviously this lambda is associated with this vector. So I mean, if you want to write a little 1 there, plus c2 v2 lambda 2 of t. Okay, well, we just found our v1 and our v2, right? They're right, see, I did it yellow, right? They're right here. And what was it? 1, -1, and 3, 2. So 3, 2, and 1, -1. So I have 3, 2. Let me just put these in right now. And this one was 1, -1. And then we have e to the lambda t, where our first lambda was 4, so 4t. And our second lambda was -1, so e to the t. Okay, so this is our general solution. I mean, we're basically done, but we can again simplify this a little bit, and you'll notice in the back of your book they'll simplify it, and they're just really multiplying all this out. So just quickly, scalar multiplication with c1 and e to the 4t. So I have 3c1 e to the 4t, 2c1 e to the 4t. I'm going to end up adding here. So plus c2, and then I have, well, okay, let's just not skip steps. E to the -t, e to the -t, and then of course our vector, our matrix addition. So we have 3c1 e to the 4t plus c2 e to the -t, 2c1 e to the 4t minus c2 e to the -t. So that is our general solution, x of t. So hopefully that makes sense. I know it's a little bit long, but again, the math is not too bad. You're working at matrices, systems, and I mean, characteristic equation, basically it's a polynomial equation, which is very, very nice because we know how to factor. Okay, I'll see you in the next video.